All right, so last week we already gone through how to predict a double replacement reaction. So we're going to learn how to predict the other types of reactions today. So, a synthesis reaction. Whenever two elements are reacted together, there's really only one thing that they can do. They're going to bond. Right? So, if it's a metal, if there's a nonmetal, you need to look up the charges and make sure that your ionic compound is neutral. I've kind of stressed this over and over again. Your ionic compound must be neutral. You have to make sure you have the right number of each of them to make that happen. For nonmetals, nonmetals can have different numbers of charges as you see when you look at your charge sheet. But you can still do it because in general, you're looking at prefixes. If you have two nonmetals bonded together, then you'll be able to come up with some kind of combination as long as it makes sense. As long as the charge is correct, you should be able to figure it out. So let's just go through and do some examples. If magnesium and oxygen react. Okay, so these two metals, I got a metal, I got a nonmetal. When I look up the charges, magnesium is +2, oxygen is -2. So the simplest way for that to come together is MgO. Now, again, oxygen is a diatomic element, which means when it's alone and unbonded, it has a subscript of 2. But if they are bonded, that rule goes away. So we don't just write MgO2 just because O had a 2 over here. Okay, you have to kind of reevaluate what the compound should be. So once you've figured out that that's the compound, then you just go ahead and balance it, and that's it. So predicting the product of a metal and a nonmetal should be just as easy as combining the charges. Okay? And for each of these, we're going to do several examples here towards the end. So like for this one, if I combine aluminum and chlorine, that's a metal with a nonmetal. You have to look up the charges to see what these could form. So charge on aluminum, what it bonds? What do you guys think? It's going to be +3. So if that's a +3, and the charge on chlorine? -1. Okay, so aluminum, chlorine, a +3, a -1. That means I'm going to need 3 chlorines to make that compound happen. All right, so the compound is neutral. Now we just go ahead and balance. We've seen this before, a similar pattern where you have chlorine in increments of 2, but chlorine in increments of 3. So in that case, you'll have to use lowest common multiple, which would be 6. So 2 there, 3 there, and then the 2 there. Okay, try the next one between calcium and phosphorus. Okay, anybody got a product for me? What's it going to be? Renee? That's right. So let's go over that. Phosphorus carries a charge of -3, and calcium would be a +2. So you need +6 and -6 in each compound. So to get that, multiply the calcium by 3. That gives us +6. Multiply the phosphorus by 2, by 2. That gives us -6. Okay, and then we balance. So 3 here, and then 2 there. Okay, so that's synthesis, neutral compounds. Okay. Single replacement. Remember that a single replacement is when you have an element and a compound reacting together. One element will replace another element. So again, the compound must be neutral. Metals replace metals. Non-metals replace non-metals. So if KBr were to react with chlorine, chlorine has a subscript of 2 because it's one of the 7 diatomic elements. To answer this question, you need to realize that chlorine is a nonmetal, so therefore the nonmetal will go in, bromine will get pushed out, which means our compound will be K with Cl and bromine on its own, but it's not really on its own because it's a diatomic element, so it's Br2. K is a +1, Cl is a -1, so that compound works out that way. Okay, so that's an example of nonmetal replacing nonmetal. Let's try this one. See if we can figure it out. Yeah, Shiv? That's right. So in this case, barium is a metal, sodium is a metal. Sodium will get pushed out. Barium is a +2, sulfate is a -2, and sodium on its own has no charge.
Two very different teaching styles on these sides of the walls.
What if we mixed iron and strontium oxide? So iron, they're telling you the charge will be 3. Okay, so you would start out by writing iron. Now, when you write iron alone, whenever you write the element alone, you don't write the 3 charge. That 3 charge is there to tell you what it's going to be when it is in a compound. Does that make sense? All right, so it's like the 3 is not useful to writing what the symbol of the element is, but it will be useful when we write the product. Okay, strontium oxide. We look up strontium. It's a +2. Oxygen is a -2. So that's how we write that. Now you notice the difference here is that here I gave you the names, whereas in the previous example I gave you formulas. If you are given the names, you can still do this. You just have to write the formulas first, and then you have to predict what the formulas of the products will be. So now that we have our formulas, what's my formula going to be? What gets pushed out? Sr gets pushed out because that's a metal. Okay, iron is a metal, Sr is a metal. So Fe with a charge of 3, oxygen with a charge of -2. So we'll put 2 there and put a 3 there. You can almost see, I don't know if you guys have picked up on it, there's kind of like a crisscross pattern with what the charge is and what the subscript is. Okay, now you have to be careful about that though, because with ionic compounds, you must always write the lowest ratio. So if you had like a 4 and a 6, your subscripts would not be 4 and 6. They would be what? They would be 2 and 3, yeah. Yes?
I put Fe2O3 plus SR.
Sorry, say again?
I put Fe2O3 plus SR. Same thing, right?
Yeah, it's the same thing. All right, so to balance this, 3 there, 3 there, 2 there. Okay. So that's how we balance single replacements. For combustion reactions, first of all, you need to realize it's a combustion. So you need to know that the pattern is a hydrocarbon. Remember, hydrocarbon is any compound that contains a bunch of C's, a bunch of H's, and it might include another element, typically O, but that O does not need to be there, but it could be there. So, a hydrocarbon reacting with oxygen. This is pretty easy because the products are always going to be the same. Combustion will always produce the same products. It's always going to be carbon dioxide and water. So, really, the hardest part about combustion is the balancing sometimes, because you get a lot of halves with this one. So, let's balance methane. The specific pattern of balancing for hydrocarbons is what? What do you start with? Okay, so one carbon, done. What's your second element that you start with? Hydrogen. Okay, so I've got 4 H's on the left. Currently, I have 2 H's on the right. So if we put a 2 here, that fixes our hydrogen. All right, and then the only other element that we have not addressed is oxygen. So 2 O's here, 2 O's here, makes for a total of 4 O's on the product side. Okay, to get 4 O's on the reactant side, you just needed 2. Okay. So let's try butane. Or rather, you try butane. See what you come up with. So, anyone care to share? Dylan?
2C4H10 plus 9O2, which is 8CO2 and 10H2O.
Okay. Let's double check here. Okay. I like most of your numbers. I'm going to make one adjustment. Okay, let's talk through this. So, carbons. So, 8 carbons, 20 H's, 10 O's plus 2 times 8, which is 16, so 16 plus 10, 26. Okay, and the reason why we had to escalate this here is because this came out originally to 6.5, but you can't leave a decimal value in your balanced equation. Let's try the next one. Alcohols are tricky because there's an oxygen that kind of hides in there in the formula, so don't forget about that guy. Okay, so if we start with carbon, you got 5 on the left. Let's use a 5 on the right. We move to hydrogen next. We got 12 hydrogens on the left. So put a 6 here in front of water. That gives us 12 on the right. So now we're oxygens. 6 O's plus 2 times 5, 10. So 10 plus 6 is 16. So we're going to need 16 on the left. But here's the problem. It comes in increments of 2, but there's also this guy hiding in here. So if I just put an 8 here, 8 times 2 would be 16 plus 1, that would be 17. So I can't just put an 8. So if I did a 7.5 times 2 to give me 15, I can add the 1 here, and that would be a total of 16. So now these are the right proportions, but we can't leave it this way, so now we double everything. So 2, 15, 10, and 8. I mean, whoops, that 12. Okay, combustions, the hardest part about combustion is not predicting the products, it's balancing. Okay? All right, so about decomposition. Remember that decomposition is when you only have one reactant, right? And it breaks down. So you're not going to be asked how to predict these because there is a myriad of possible products that could turn into, and frankly, you haven't had enough background yet to be able to do this properly. So you'll have to predict the products of 4 of the 5 types. All right, so all the others except for this one. Okay, so we have a bunch of scenarios here, which some of them tell you what they are, some of them don't. So we're going to take some time in class. You're going to work through these, and then we'll come back and reconvene, and then we'll see how we did. So